Welcome to the video for lesson 2.3. This lesson introduces moments and moment generating functions. First of all, I'll begin by defining moments of a discrete distribution. In our last lesson, we learned how to find the expected value of any function of a random variable x. If we consider the functions x, x squared, x cubed, and so on, the expected value of these functions are called the moments of the distribution of x. We call the expected value of x the first moment of x, the expected value of x squared the second moment of x, and so on, with the expected value of x to the rth power called the rth moment of x. We've already seen two of these moments in the formulas for the mean and the variance. The mean, remember, is the expected value of x, and although we saw that the variance is defined as the expected value of x minus the mean squared, it can be computed more easily by using the fact that this quantity is equal to the expected value of x squared plus the second moment of x minus the mean squared. One thing to note is that for some distributions, not all of the moments might be finite. Now we'll talk about moment generating functions. For some distributions, special functions called moment generating functions can be defined. In some instances, moment generating functions give an easier way to calculate the mean and the variance of a distribution. Moment generating functions can also be used to determine the distribution of a random variable. And later in the course, we will use moment generating functions again to help us to find the distribution of sums of independent random variables. We'll see that in chapter 5. Now let's define the moment generating function. If x is a discrete random variable with probability mass function little f of x and support s, then the moment generating function of x is given by, we use the notation capital M of t, and it's equal to the expected value of e raised to the t times x power, which we could find by calculating e to the tx multiplied by the probability mass function f of x for each value in the support and adding them up. And as long as the sum is finite for some interval of t around 0, this is called the moment generating function. If the sum is not finite for an interval of t around 0, then the moment generating function of x does not exist. So not all discrete random variables have moment generating functions. However, when a random variable does have a moment generating function, then we can use that moment generating function to find the moments, thus the name moment generating function. If the moment generating function exists, we can find the rth moment of x by taking the rth derivative of the moment generating function and evaluating it at t equals 0. In particular, we can find the mean and the variance with the moment generating function. Since the mean is equal to the expected value of x, which is the first moment, I can find it by taking the first derivative of the moment generating function with respect to t and then evaluating it at 0. Now the variance is the expected value of x squared, that's the second moment, so that would be the second derivative of the moment generating function, evaluated at 0, and then I subtract off the expected value of x quantity squared, that's the mean squared, which we already said we could find using the first derivative of the moment generating function evaluated at 0. So using the moment generating function and taking a couple of derivatives, we can find the mean and the variance of the discrete random variable x. We'll do an example. We're going to find the mean and the variance of the random variable x that has moment generating function m of t equals 2/10 plus 1/10 times e to the t power plus 2/10 times e to the 3t power plus 5/10 times e to the 4t power. We're going to start by taking the first derivative of the moment generating function. Then we're we're going to evaluate that derivative at t equals 0. And that gives us the mean. Now, to find the variance, we are going to need to take the second derivative of the moment generating function. Now we're going to evaluate the second derivative at t equals 0 to get the expected value of x squared. And finally, we will find the variance by taking the expected value of x squared minus the mean squared, and that gives us our variance. Now, the other thing we can do with the moment generating function is use it to find the probability mass function. If the support of x is the set of numbers b sub 1, b sub 2, b sub 3, and so on, then the moment generating function, remember, is given by m of t equals the expected value of e to the t times x power, which could be written as the sum e raised to the t times b1 power times the PMF evaluated at b sub 1 plus e to the t times b2 power times f of b2 plus e raised to the t times b3 power times f of b3, and so on. Notice that we can find the support by looking at the exponents of our moment generating function and taking the constants that are multiplied by t in each of those exponential terms. So there's our support. And also notice that we can find the probability of x taking on each of those values in the coefficients for those terms. So the coefficient of e raised to the t times bi power must be equal to the PMF, little f, of b sub I. Once again, we will do an example using the moment generating function to find the probability mass function. We're going to find the probability mass function of the random variable x that has moment generating function m of t equals 2/10 plus 1/10 times e to the t power plus 2/10 times e to the 3t power plus 5/10 times e to the 4t power. Okay, so first of all, we have to notice that when we see a constant term like 2/10, that we could re-express 2/10 as 2/10 times e to the 0t power. So the moment generating function could be re-expressed this way. Now I am going to circle the support. Those are the coefficients that I'm multiplying by t in the exponential terms here. So we have 0, 1, 3, and 4 that are in the support. So if I want to write my PMF as a table, I could write it with my values of x and little f of x, my probability mass function at those values. I know my values of x in the support are 0, 1, 3, and 4. Next I need to find the probability associated with each of them. Remember that the probability associated with 0 is going to be the coefficient here, so that's 2/10. The probability associated with 1 is the coefficient, 1/10. The probability associated with 3 is this coefficient, 2/10. And the probability associated with 4 is the coefficient we see here, 5/10. And that is the probability mass function for the random variable x that has this moment generating function. I hope this video has been helpful getting you started working with moment generating functions. Have a good day.